Okay, so the situation here, um, Mrs. Maddie's video production club has 10 students. She asked them, how many movies did you stream in the last year? And so the 10 students gave these responses, right? So student one streamed 32 movies, student two, 18, and so on. Okay, so we have a big set of data, but again, just looking at 10 numbers, it's kind of a blur. It's hard to get info out of it. So we can use our measures of center or spread to sort of describe the data. So first, let's use just regular range. Okay, so let's remember that regular range is simply the max minus the min, the biggest number minus the smallest number. Okay, so you want to make sure that you check if the values are in order or not. These are not in order, so we got to find. Looks like the biggest number is 41, and the smallest number is 9. Okay, so the range is 32. All right, so in a sentence, what this means is the person who watched the most movies watched 32 more than the person who watched the least movies, right? 41 minus 9 means 32 more. Okay, but one of those members noticed the range as a statistical measure is kind of limited, right? Because there would be no difference between this data set and like this one or like this one, right? These all have the same range of 32. Because if you ignore the middle, you only use the maximum and the minimum, right? So the range is not a perfect measure of spread because, again, it ignores the middle. Okay, so she wants a measure that does include the middle of the data. Okay, so she's still looking for dispersing. So disperse means to like spread out. Okay, so a measure of spread that does include the middle is the standard deviation. Okay, so let's review that one since that one involves a lot of calculations. Right, so the first thing you need to do is find the mean of the original data. Right, I say original because we're gonna do some stuff with it. So then we're gonna have different data later. Okay, so to find the mean, you add up all the data points and divide by the amount of data. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh yeah, it told us there's 10, sorry. Okay, just a reminder, if you're using your calculator, you need to make sure you add the numerator first and then divide by 10. Okay, so I would recommend typing it in with parentheses around the entire numerator. Otherwise, only the 26 will get divided by the 10 when you want all the data points to get divided. Okay, so I'll just go ahead and tell those of you without a calculator. This should come out to 23. Okay, so the mean number of movies watched was 23 per student. Okay, so then what we do from there, uh, okay, so we take the original data again. Sorry, this might be a little bit cramped. So let's just copy down the original data points. Okay, so again, I've just copied the original data down. I guess you could have done this horizontally. It might have been a smarter uh, strategy, but sorry, I didn't think about it. Okay, so that's the original data. You can label it if you want. Okay, the next thing we need to compute is the distance from mean. Okay, and as a reminder, we just calculated that the mean is 23. Okay, so the nice thing here is when we talk about distance, we don't care about positive or negative, right? You don't say something is negative 5 feet away from you. It's just 5 feet away from you. Okay, so you just subtract the original data value and the mean, but again, you don't need to worry about positive or negative, right? So like 32 minus 23 is 9. Then you can switch it up. 23 minus 18 is 5. 23 minus 15 is 8. 27 minus 23 would be 4. 24 minus 23, just 1, and so on. Okay, and then the reason that we don't need to be concerned about whether it was positive or negative is because we're now going to square those distances, right? So when you multiply a number by itself, it doesn't matter if it was positive or negative, it is going to turn positive anyways. So these distances from the mean, they're called deviations. Like when you deviate, you sort of stray from the intended path. Okay, so you're now going to multiply each of these numbers by themselves. Okay, and then next you find the mean of the deviations, right? So that's why earlier I specified that that was the mean of the original data, because now we're going to do the mean of this column, which is actually the square of the deviations. So we'll just say the mean of the squares. All right, so you'd have to add all of these up. So it'll be the same number of data points, right? Because you did one for each original data point. Okay, so this should come out to 76.6. Okay, and then lastly, to find the standard deviation, you want to basically undo the step where you squared it, where you multiplied it by itself. Right, so the opposite operation of squaring is square rooting. Okay, so to get the standard deviation, you square root that previous answer. Okay, and I'll just round to the second decimal digit. Okay, so yeah, standard deviation, unfortunately, it is a extremely long calculation, right? The individual steps aren't too bad, hopefully, right? It's just adding, dividing, squaring, square rooting at the end using your calculator. But yeah, the standard deviation is a very valuable statistical measure because, again, it tells you how spread out the data is. It tells you, is the data very close to the mean or is it very spread out? Are their data values very far from the mean? Okay. So before we continue, let me see if there's questions about anything so far. Okay, so a nice thing about the standard deviation and what's called the normal curve or bell curve or Gaussian curve is you can use it to compare different things against each other, even if their values are different. Right. So, for example, if you want to compare, like, I don't know, a pro basketball team against a college basketball team, it might seem impossible because, like, the pro game is 48 minutes, the college game is 40 minutes, and there's other differences. But if you standardize them with a normal curve, then you might potentially be able to compare, various aspects. Okay, so to do that, we need to be able to calculate what's called a z-score. Okay, so the z-score formula, you say this out loud as x bar. It's in capital X with like a flat line over the top, minus the Greek letter mu. So it sort of looks like a cursive U, over sigma. Okay, so what do each of these things represent? X bar represents the sample value. Okay, so that means the value that you're working with right now. Mu is the mean, again, the average value. Okay, and then sigma is going to be your standard deviation. Okay, so just be aware that if you continue on with statistics, at some point you may see a formula that looks like this instead. It's beyond the scope of what we're going to cover in this class, so you don't need to know this one. But basically, we're looking at the situation where n is 1, right? Because if n is 1, then square root of 1 is still 1, and dividing by 1 stays the same. Okay, so yeah, if you see this in the future, we're just using like a simplified version of it, basically. Okay, so yeah, just be aware of that. Okay, so yeah, you use this formula to get what's called a z-score, but we want to understand what a z-score actually represents. Okay, so a z-score represents the number of standard deviations either above or below the mean. Okay, so when the z-score is positive, that means above the mean. When the z-score is negative, that means below the mean. Okay, so again, you can only do these things for numerical data, things like, how many years old, how many inches tall, how many questions correct on a test, right? Those are all numbers. You could not do the standard deviation for something, or the z-score for something like, what's your favorite color, right? Because like, the data score of green, you can't, subtract green from orange or anything like that. Okay, so let's do some examples of calculating z-scores. Okay, there's 220 sixth graders on this trip. The mean or average height is 56 inches, standard deviation of 3 inches. Okay, so now we're not looking at all 226 graders. If we just look at one specific camper whose height is 62 inches, what is that camper's z-score? Okay, so again, we're going to want the formula above. Okay, but let's identify what each of these things represent. Okay, so the camper's heights have a mean of 56 inches. Okay, so remember the mean is a sigma, the cursive U looking thing. Okay, so for this problem, mu equals 56 from the yellow highlighted part. Next, the standard deviation is 3 inches. So standard deviation is like the denominator. Okay, so for this problem, sigma will be 3. Okay, and then the one camper that we're calculating right now, they have a height of 62 inches. So that'll be your X bar. Okay, so let's just go and substitute all those values in. X bar is 62 minus mu, the mean, which we were given as 56, and divided by the standard deviation sigma, which we were told is 3. Okay, so again, let me just quickly show you that parentheses matter. Right, if you just type in 62 minus 56 divided by 3, this is not the right answer, right? Because what your calculator does is order of operations. It does 56 divided by 3 first, and then it takes that answer minus the 62. Okay, so in order to group the 62 minus 56 together, you need to put parentheses around it, right? And then outside the parentheses, you divide by 3. Okay, so the correct answer is positive 2. Okay, so the z-score is 2, but what does that mean? Okay, so again, the z-score refers to the number of standard deviations above or below the mean. In this case, it's a positive number, so it'll be above the mean, which makes sense, right? The camper is 62, the average is 56, so clearly this camper is taller than average. Okay, so now let's say there's a different camper. Their z-score is negative 0.5. Okay, so negative z-scores mean below the mean. Okay, so this student is slightly shorter than average. Okay, so the way we would phrase that, this camper's height is 0.5 standard deviations below the mean. Okay, and then we're asked to find that person's actual height. Okay, so it's going to be the same formula as above, but we're going to be told different things. Okay, so let's copy down the formula. Okay, so this time they tell us the z-score. They tell us the z-score is negative 0.5. So you're going to plug that in over on this side of the equation. Okay, and make sure you include the negative. Okay, what we don't know is this student's height. All right, so x bar is the unknown this time. So leave that as the variable. Okay, but we're still dealing with the same group of students. So the average mu, the average is still, oh, sorry, not that. The average is still 56 inches. And the standard deviation is still 3. Okay, so you should only have one variable left, and that's what we have here, right? If you had two different letters, that would mean that you are missing some information. Okay, so now we just need to get the unknown by itself. I would start by getting rid of the divide by 3, the denominator. So to cancel out a divide by 3, the opposite would be to multiply by 3. And because it's an equation, to keep it balanced, you need to multiply both sides by that number. Okay, so simplifying 3 times the left side of negative 0.5, we get negative 1.5. Okay, and then to get rid of the minus 56, we now add 56 to both sides of the equation. Okay, so we now have the height of the student. Okay, so any questions on any part of the front page? Okay. Moving on to the second page then. Okay, so here we have a different ride, right? Different rides had different height requirements. So for this one, they must be at least 51 inches tall. Okay, so it's the same group of students. The mean is still 56. The standard deviation is still 3. All right, but we want to know what percentage of students will not be allowed to ride. Okay, so same formula. All right, the z-score equals, in the numerator, x bar minus mu all over sigma. Okay, so this time the height we care about is 51. All right, so that's our x bar. The mean is still, oops, sorry, the mean is still 56, so that's still going to be mu. The standard deviation is still 3, so that's going to be sigma. Okay, so 51 minus 56 all over 3. Okay, so 51 minus 56 is negative 5, and then negative 5 divided by 3. The decimals go on forever, so I'll round to negative 1.67. All right, so now we're not done yet. The question was not what is the z-score? This time the question is, what percentage of students will not be allowed to ride due to not meeting the height requirement? Okay, so here's the really good thing about the normal distribution. Whether you're comparing heights or test scores or age or weight or anything else that's normally distributed, like a z-score of 2 means the exact same thing for all those situations. Okay, so regardless of the real life context, the numbers always mean the same thing. Okay, so what do we do with these? So let's go ahead and draw like a bell curve. Yeah, again, you've seen this shape before, often in the context of grades. Okay, and so what we want to do is mark this z-score of negative 1.67. Okay, so what you need to know is that on the bell curve, 0 is right in the middle. Okay, but then we don't have 0, we have a negative number. So negative numbers are to the left of the middle. Okay, so let's just mark it like right here. Okay, so what you want to do is figure out, do you care about this part of the curve to the left or this part of the curve to the right? And it's going to change from problem to problem. Sometimes it'll be left, sometimes it'll be right. So you need to read the situation. In this problem, we want to know what percentage of students cannot ride. And the students who can't ride means that they're shorter than this height. Okay, so to figure out how many students are shorter, that means their height is lower, so you want to the left. All right, so go ahead and shade in the part of the curve to the left of that line. Okay, so how do you know what to do with this? Well, let's go ahead and flip to the third page. Okay, so here's what's called a z-table. It tells you the area to the left of various z-scores. Okay, so like what this means is that a z-score of, let's just say, 0.73. Okay, so if you had something like this, okay, so this time 0.73 is a positive number. So let's draw the vertical line to the right of the middle. Okay, what you would do is the unit and the ones and the tens place come from the left column, right? So because it starts 0.7, you would look for 0.7. Okay, here it is. And then the hundredths digit is from the top columns. Okay, so the hundredths digit is a 3, so you would look for the 3, the 0.03. Okay, and then now you find where they intersect. Okay, so if you look up 0.73 as a z-score, the table tells you 0.7673. Okay, so what that means is that the area to the left is 0.7673. Okay, so let me explain in words what this means. Okay, so if you want to convert that decimal to percent form, you just multiply by 100, move it twice. Okay, so 76.73% of values are to the left, meaning less than a z-score of 0.73. Okay, so let's just say that on a test, a teacher told you, oh, your z-score was 0.73. What that means is that 76.73% of other students scored lower than you, right? Because that's the area to the left, meaning these people all scored lower than you. Okay, so again, the 0.73 was just a random number. Now let's get back to our problem. Okay, so here our z-score was negative 1.67. Okay, so we're going to want to look up negative 1.67 on our table. But you might notice this table does not have negative numbers on it. Okay, so what do? You would need to flip the curve horizontally. Okay, so again, you can imagine you grab this and you like flip it around. Okay, so you're allowed to do that because the normal curve, the bell curve, is symmetric. It's like a mirror image. Okay, so this end will flip over here. Okay, but when you do that, this flips over to the positive side. So this flips from negative 1.67 to positive 1.67. Okay, but then you also flip the shaded part, right? It's no longer the area to the left because when you flip it over, now it's the area to the right. Okay, so make sure you agree that these are the same area, right? It's just you flipped it around, but it's still the same part of the curve. Okay, so the reason we do that is we can look up positive 1.67. Okay, so back on our table. So the ones and the tenths digit are 1.6. And then the hundredths digit was 7. Okay, so 1.67 is going to be right here. Okay, but let's make sure we understand what this number means. This number is always the area to the left of your z-score. Okay, so to the left of 1.67 is 0.9525. Okay, so back over here. Okay, the area to the left is 0.9525. But if you look at our little sketch, that's not the area we wanted, right? We did not want this part, we want this part. Okay, so we have one last calculation to do. So the normal curve has a total area of one hole, right? Because that represents 100%. Okay, so this part plus this part makes up the full curve. So together they must add up to one hole. So to get the missing piece, you would just do 1 minus this, right? That'll get you the leftover. Okay, so I'll write that in words. Let's see, sorry. Okay, so again, the the empty part, the unshaded part, the table total is 0.9525. The shaded part is the part we actually want. So that means to find this shaded area, you're going to do 1.0 minus 0.9525. Okay, you can add some extra zeros to make your decimal line up. Okay, so that means that this area has a decimal value of 0.0475, or in decimal form, again, you just move the decimal point twice, 4.75%. Okay, so that answers the question. What percentage of students will not be allowed to ride? 4.75% won't be able to go on the ride because they don't meet the minimum height requirement. Okay, so of the 220 in the group, how many students is that? Okay, so 4.75% of the 220. To find a percent of a whole, you multiply. Okay, so 220 total minus, and we'll go back to using the decimal form. Okay, so of course, when we're dealing with students, you have to have a whole number. So we'll just round to the nearest whole number, which is 10. Okay, so the next example is going to be very similar. So we'll start it together, and then you'll have the chance to try applying it to see if you are um, able to do this type of calculation. Okay, so now we're talking about vacation expenses, how much a vacation cost. Okay, so normal distribution, mean 2,313, standard deviation 390. Okay, so first question, what percent of families took vacations that cost below 2,000? Okay, so we want to find the z-score, right? The cost we care about is 2,000, so that's our x bar. Minus mu, the mean. We were told the mean is 2,313, and standard deviation we were told is 390. Okay, so we've got our z-score, negative 0.80. Okay, so I'm going to sketch a little bell curve again. Because the z-score is negative, I'll draw my dividing vertical line to the left of the middle. Okay, and then now I need to know, do I shade to the left or to the right? In this case, we want to be below 2,000. So below is less than, which means to the left, right? So we want to figure out the area to the left of the z-score of negative 0.80. Okay, so I'm going to ask you to try to take it from here. Okay, so again, use the example above, use the table on the next page, and make sure you answer the final question, which is what percent of families took vacations that cost below 2,000? Okay, so our z-score is again negative, which means that because our table doesn't have negatives, just like on the first example, we need to reflect it. Okay, so when you flip it over, the negative 0.8 flips over to the right side, so it becomes positive 0.08, sorry, 0.80. But the shaded portion is always the little part. So it's not this, it's over here. Okay, I didn't really draw it perfectly, but that's fine. Okay, so now we're able to look up positive 0.80. Okay, 0.80 means that to the left is 0.7881. Okay, so again, to the left of our vertical line, the table says 0.7881. Okay, so for some problems, this might be the answer. If the question had been, if the original problem had been what percent are greater, when you flip it, it would be over here and you would be done. Okay, but that's not what we have, right? So here we again need to subtract from one whole. Okay, and then lastly, to convert to percent form, we move the decimal point twice. Okay, 21.19% of families took vacations that cost below $2,000. Okay, so parts B and C are also based on the z-scores and the table. Okay, so go ahead and now see if you can do the next two parts of this question, please. Okay, so again, you should draw a sketch. Okay, for letter B, now we want to consider families whose vacation costs more than 3,000. Okay, so the only thing that changes is X bar, the number we care about. The mean is still the same and the standard deviation is still the same. Okay, so this time we get a positive z-score of 1.76. Okay, so positive numbers are to the right of the middle. Okay, and now we decide, are we caring about the values less than it or more than it? We want to know about above, so that means we care about more than. Okay, so that's why I shade to the right this time. Okay, I don't need to flip it over because it's already positive, but I'll go ahead and look up 1.76 on the table. 1.76 tells me that to the left is 0.9608. Okay, and now I see, is this the number I wanted or do I need to subtract from one? The area to the left is the unshaded part. I always want the shaded part. Okay, so yet again, I need to subtract from one full. Okay, again, you won't always subtract from one. It's just a coincidence that so far, all of them have been subtract from one. You won't always subtract from one. Okay, so the decimal form is 0.0392. So in percent form, you move the decimal twice, 3.92%. Okay, and then lastly, we have a question about what percent have vacations that cost between 2,000 and 3,000. Okay, so those numbers are familiar, right? We already worked with 2,000, we already worked with 3,000. Okay, so actually for this one, you don't really need the table at all. You just need your first two answers. All right, so we know that the cost of 2,000 had a z-score of negative, sorry, let me redraw that, negative 0.80. Okay, and we've already calculated that that area was 21.19%. And then on the previous problem over here, right, we already know that the value of 3,000 corresponds to the z-score of 1.76. And we've already calculated that the area to the right is 0.392, or sorry, 3.92%. Okay, now what area do we want for this part C? We want between them. So between them would be right here. Okay, so this time the curve has been split into three pieces, but still they must all add up to 100, one whole or 100%. Okay, so, right, the total curve is 100%. If you subtract away the blue portion, you have 78.81%. And then now if you subtract away the pink portion, you're left with 74.89%. Right, because those are the only three options, right? Either the vacation costs less than 2,000, between 2,000 and 3,000, or more than 3,000, right? Those three combined are the only possible scenarios. So that's why they have to add up to 100%. Okay, so yeah, that's one way you can do this. Okay, so we have one last situation. Okay, so a hotel gets a rating from 1 through 100. They rated over 2,000 hotels. Ratings are normally distributed, mean 78, standard deviation 6.5. What does the rating need to be for it to be considered in the top 10%? Okay, so how do we do this? So here's our z-score formula as usual. Okay, so we don't know the hotel's rating, right? We don't know X bar, so that's still unknown. But we do know the mean is 78. Oh, sorry. And we do know the standard deviation is 6.5. Okay, but what is the z-score? Well, we want it to be in the top 10%. Okay, so what does it mean to be in the top 10%? Top 10% means that whatever score it is, you'd have 0.9 to the left, right? That means 90% of other hotel scores are below yours, right? And only 10%, 0.1, are above yours. Okay, so we basically need to find the z-score that has 90% to the left, 0.9 to the left. Okay, so let's go to the table. But we're going to use it kind of backwards from before, right? We're not looking up 0.9 on the outside, right? Because we want the area. We want the inside to be 0.9. Okay, so look at, the inside and try to find 0.9 or as close as possible. Okay, so to me, this looks like the closest number to 0.9, 0.8997. Okay, so what z-score does this? 1.28. Okay, so make sure you understand a z-score of 1.28 has 90% of values to the left, right? So that means that if your z-score is 1.28, 90% of hotels scored lower than you, which means you are top 10%. Okay, so for that reason, the z-score we need is 1.28. So again, we looked up on the table and we found that the z-score, which splits up the curve the way we need, with 90% less, is 1.28. Okay, so back in the formula, we can replace z with 1.28. Okay, and now you just need to get the variable by itself. So first, you may wish to get rid of the denominator. So to get rid of the divide by 6.5, we can multiply both sides of the equation by 6.5. Okay, so 6.5 times 1.28. Okay, and then to get rid of the minus 78, we add 78 to both sides. Okay, so if a hotel scored 86.32, their Z score would be 1.28, which means that 90% of scores are below, so that would put them in the top 10%. Now, it says that the scores can only be integers, so basically whole numbers. So that means that we would probably round this to the next number up, right? So 87, right? You don't want to do 86 because that would mean that less than 90% is to the left. So you want to go further up. All right. So questions on any of this? Okay. So